Hello and welcome to this class of the continuation for the spectrochemical methods, where we will just looking at some chromophoric groups, because that is very much essential to generate color to the solution. So, how we can generate that particular solution color, so that we can estimate the unknown amount of analyte in a solution by looking at the color intensity, which will be directly proportional to the concentration as per Beer's law. So, we have also seen that when this particular chromophoric part, it can also present to the analyte itself, and at the same time, if we consider that, as we discussed, that it can have a very good azo function in it, the organic molecule containing azo function or the amine function, and this particular group we have discussed in detail in terms of the acid base titration reactions, that these are the typical backbone for different acid base indicators. So, what we see here, that this particular azo function along with some kind of conjugation in the corresponding benzenoid part or the corresponding quinonoid part, as we know in case of methyl red and methyl orange. Only variation is their substitutions. Okay. So, a long range of color variations starting from red to yellow or orange to yellow for these, one is in the acid form and another is in the basic form. What we find? So, if this particular species is present, so if the analyte itself contains this particular chromophoric group, that means this chromophoric group is present in the analyte itself. So, we can measure the unknown concentration of these two as well. So, the corresponding presence of these groups, which will be responsible for absorption of electromagnetic radiation in a particular range, in particular the visible and the UV range. So, these particular molecules can be identified very nicely by looking at the corresponding absorption of radiation. But in some other case, what you find that there will be some chromophores or the metal ions, like say aluminum 3 plus. In solution, we know this is not a d metal ion or the transition metal ion having unpaired electrons in the d levels. So, in solution color, it is colorless. So, how do we measure the corresponding concentration of this Al3 plus when Al3 plus is your analyte? So, our unknown analyte is aluminum, trivalent aluminum ion. So, it is colorless. So, as I told you in our previous class, that if we add something, that means this chromophoric group, that means some reagent, and that particular reagent will give this example more in detail when we see for the other technique, that is the fluorescence technique in our future classes. So, if this particular reagent can bind to this particular species, so some molecule is known as alizarin, say alizarin is a class of organic molecules. So, alizarin itself can give rise to some color like that of our metal ion indicators. We all know what are metal ion indicators. Like these acid base indicators, the clear definition for these acid base indicator is that with the change in pH values, that means the hydrogen ion concentration in one form to the other, it can change its corresponding color. Similarly, this particular metal ion indicators, such as we know one name particularly, you should remember aerochrome black tea, Sometimes these are mostly name attached as a very commercial name, but it has some origin definitely. And you see this particular part is chrome, is not due to chromium, but is due to this particular chrome, that means the color generating function. So, this areochrome black tea, what it does, because it has again this particular an important azo function. So, this areochrome black tea can change its color, that means in one form when the metal ion is not present, that means in terms of the PM, the negative logarithm of metal ion concentration, it can vary its different color. So, in absence of this metal ion, this areochrome black tea, definitely it is in the solution, because the compound which we get like your methyl orange and methyl red, they are solid powder compounds, they are solid powder which are soluble in ethanol. So, in a mixed solvent medium, ethanol water medium, we make the typical solution for solution measurements. Similarly, areochrome black tea can also be dissolved in alcohol to get the corresponding solution, and in absence of solution that metal ion, that means in when the metal ion is not binding to your this indicator, it has one particular color, and when it is bound, it has a different color. So, what this azo function can do over there? So, we just simply know this in this particular form, that azo function can have the lone pair of electrons. So, when these lone pair of electrons are donated to the metal ion center, so only one of them can form a coordinate bond to this particular metal ion, and it has some other groups attached to it. This azo function can have the groups like this X and Y. So, it can form a good chelate to the metal ion. This metal ion is nothing but your Mn plus. So, it can form 3 bonds together to this particular metal ion, and we all know that this is a very useful technique when we go for EDTA titration, because EDTA can compete with this particular species where the metal ion is bound to the ligand, and when EDTA can take up the metal ion or can make the metal ion free from in the bound form of this particular ligand, we get the corresponding species as the free form of the ligand and the metal EDTA complex. So, what we see now is that the incorporation of this azo function, that means the binding of the metal ion, this is also your metal ion. So, your reagent, if it is alizarin, so we get some reagent, we name this, it is areochrome, this chromophoric group. So, this can be our chromophoric reagent. When we get this particular chromophoric reagent, so the species L is your alizarin, the ligand, that is now colored. So, there are large number of these species or these corresponding groups present, which can be considered as the corresponding chromophoric reagent, and this chromophoric reagent we can get in such a way that the product of this particular reaction, product of that reaction can absorb strongly in again our most interesting region of understanding, that means the UV region. Okay. So, this particular case or this particular thing, already we have learned so many things. So, if your analyte is here, then chromophoric reagents, these are chromophoric reagents. So, we can have the analyte as well as the chromophoric reagents. So, already we know that we can have Fe3 plus ion, and due to the charge transfer condition, we get a corresponding blood red coloration due to the addition of some reagent which can bind to the ferric ion, which is nothing but our thiocyanate ion. So, when this binds over there, we should also be very much careful about one particular terminology, is the interference. due to the presence of other metal ions which can also bind to this particular anion, inorganic anion, which is your chromophoric reagent, but gives a different types of color, but it can hamper the absorption of the radiation in the UV region for due to only Fe3 plus. So, what we see that not only Fe3 plus, but cobalt also in cobalt 2 plus, it can also bind to thiocyanate ion. It can also bind to molybdenum hexavalent MO6 plus. So, whenever we use all these things for the analysis for this particular say ferric ion, what we should know that when ferric ion is present and we want to use this particular method or the methodology for the determination of unknown ferric concentration, the solution should not have cobalt 2 plus or molybdenum 2 plus. In other way, what we can also state that this cobalt 2 plus, if it is present alone, can be determined in presence of this thiocyanate. In a similar fashion, if molybdenum 6 plus, the hexavalent molybdenum, we know molybdenum is present in all sorts of analytes, that means it can be present in your steel sample to molybdenum enzymes. So, a industrial sample starting from say industrial sample, the steel to the biological sample, which are molybdenum enzymes. So, in between you can have different materials and all. So, if all these can have your molybdenum center, and if we want to measure the corresponding unknown concentration of molybdenum, we can safely use thiocyanate ion for that particular purpose. So, this is useful for thiocyanate. So, in a similar way, we should know the responses what can be given by say peroxide ion. We all know that this peroxide can be very nicely converted even in your biological system by reduction of your O2 molecule. Otherwise, this peroxide can be given to the solution as your chromophoric reagent from hydrogen peroxide or its corresponding salt or in presence of some weak base. So, this can form correspondingly good peroxo compounds. We all know while we go for the detection of titanium 4 plus, again it is a very good industrial sample in terms of steel sample. Then titanium can be there, titanium as the titanium oxide. So, large number of samples to be analyzed containing titanium can be handled by this particular technique. Then vanadium 3 plus can also be analyzed by this and hexavalent chromium 6 plus, because side by side these are in the same group of the periodic table, chromium and molybdenum, and down you have tungsten. So, you see that when you determine molybdenum, so what about chromium? Chromium can give you very characteristic peroxo complex. So, all these three metal ions can give very useful peroxo compounds, and these peroxo compounds have a characteristic color. So, these peroxido complexes have characteristic colors in solution. So, what we find that this particular one, and if it is there, that means if it is a titanium 4 plus having no unpaired electron in this d level, but this is saturated with some electron, it has extra electron in the antibonding level, also it has electron compared to your O2 molecular orbitals. So, you have a typical charge transfer reaction. So, as we all know, we have already seen that how the charge transfer complexes are useful for identification, because it will have high value for your epsilon max. So, if we are able to produce some of these interactions for the peroxido complexes, so this chromium peroxido complexes, we get a corresponding charge transfer species for this color absorption. And one more interesting species what can be derived from chromium is your CrO4 2 minus and Cr2O7 2 minus, that we will see Right now, that if we go for this chromium, because this chromium for in hexavalent state, this is also in the hexavalent state, it is chromate, the chromate anion, and this is dichromate anion, which can be formed from chromium 3 plus through oxidation, and it has also some equilibrium with regard to your acid. So, if you have acid, it will go from left to right, and if you put base, it will go back to your chromate form. So, this chromate, what we can have, you see that this chromium is in hexavalent state, which is a 3D0 system. That means, no unpaired electron is present over there for its corresponding DD transition. So, you will not have any DD transition for it, but instead of that, this chromate ion, which is bound to, for convention we can write double bonded one or arrowhead for this, which is 2 minus. So, if there is any charge transfer transitions, because these will have filled electron pairs in their p levels. So, if the charge, the electronic charge can be transferred from O to chromium, we get a good charge transfer transition such that we can have an appreciable magnitude, several thousands of this epsilon max value, which will be useful for determine the unknown chromate concentration as well as the dichromate concentration. Because very soon we will see also when we have the other component like your MnO4 minus, the permanganate anion, this is also a case of 3D0 system, and again a charge transfer transition will prevail over there, but we will see how we can handle if both of them are present as a mixture. Okay. So, we are talking about these chromophoric reagents and all these. So, these are typical assembly, because all these things, these peroxide things, and also we can have this reagent as iodide ion. So, all are starting from your thiocyanate ion to peroxide ion to iodide ion, all are inorganic anions. So, these inorganic anions can be very much useful to detect some of these metal ions. So, it can react with bismuth 3 plus, then palladium 2 plus, then tellurium 3 plus. So, in solution, mostly in aqueous solution, all of them can give rise to very good coloration with these iodide ions. So, what we take the example, just now I told somewhere that aluminum can be detected by a species which is alizarin, and in all these cases what we see that your thiocyanate, your peroxide and your iodide all are inorganic anions. Now, we will move to some reagents which are very much useful, which is a typical organic molecule that is very much useful for some other type of analysis we have seen earlier. So, organic molecules if we can have, and these organic molecules will be your chromophoric reagents. So, how these organic molecules can be chromophoric reagent? One example we have seen just now, that it can have an azo function, and if these azo groups, the azo molecules, because there are large number of groups of molecules are known which are azo dyes, because these azo dyes are very much useful for dyeing fabrics, for dyeing different materials, because these are in the category of paints and pigments because of this azo function. So, if a typical organic molecule can give rise to this particular information, so we get something where we get some color reagent. So, one such example we already discussed. So, it will be very easy to understand by you that your DMG molecule, which is useful for detection of Ni2 plus, so nickel 2 plus, and we all know that the combination of this DMG in with Ni2 plus in ammoniacal medium can be a precipitate. So, is rose red precipitate. So, gravimetric estimation can be also useful, but that color now we can utilize that coloration. That means, in very dilute solution, if we try to avoid this particular precipitation, we can have this rose red coloration in solution. So, once we can develop some coloration or color in solution, we can measure that unknown intensity of that color related to the concentration of either Ni2 plus or DMG for its corresponding detection as a corresponding spectrometric method for identification of unknown analyte. So, when we get this particular nickel 2 plus for this titration, we usually get this as your photometric determination. Okay. So, this is a photometric determination where this DMG H2 it has two dissociable protons. You make the solution, because in the laboratory we get this as a available solution in a dilute ethanolic solution, because initially we dissolve the solid powder is a white powder compound. We dissolve in ethanol and then dilute with some amount of water. Sometimes it can be 1:4 or 1:5 or 1:10 even. That means 10 milliliter of alcohol is fine to dissolve that corresponding amount of DMG, and which is diluted to 100 milliliter. Now, if you see this particular color, and if some small particles, because we have seen that this particular product is insoluble in water. So, it is insoluble in water. So, what precaution we should take for avoiding this precipitation of this one? If we try to do this is in aqueous solution and this is in alcoholic aqueous medium. So, we should avoid that thing in such a way that we can take something where you have this aqueous Ni2 plus, and we will take this in some other solvent. One such good example of that solvent is your chloroform, because this is also soluble in chloroform. So, if nickel 2 plus is present, and we can go for, as we all know, this aqueous medium, that means the water medium, and this particular CHCl3 medium, this can form two separate layers. So, that means this aqueous layer of this nickel 2 plus can be extracted into an corresponding chloroform solution of DMGH, which having some chelating reagent. So, aqueous solution can be extracted into a CHCl3 solution of this DMG. That means, the CHCl3 solution of your chelating ligand, because this chelating ligand is present in your this particular chloroform and forming some immiscible organic layer. Organic layer. That means, whatever nickel you have, you can use a separating funnel also, or you can use something in a test tube also. So, you have this as the aqueous layer of it. If we can extract it with the corresponding CHCl3. So, what you get? You get a CHCl3 solution of your NiL2. That means, the nickel DMG complex soluble in chloroform. So, the color intensity of that. So, the same rose red coloration can be there in this particular organic layer, and that organic layer we can put in the spectrophotometer to determine the unknown concentration of nickel in that particular species. So, what we do? We do the corresponding use of this organic molecule as again some chromophoric reagent to develop some coloration. So, we quickly will see two more examples of those groups which can be very much useful for our analysis. One is, it is the ethyl function attached to your nitrogen. So, it is the diethyl function. So, if we take diethyl amine, we can use that particular one in basic medium and react it with carbon disulfide to get something chelating ligand, where the sulfur atoms can bind to a particular metal ion center. So, this sodium salt, if we use sodium hydroxide for this preparation, it is known as diethyl ET2, because these ET2 functions are present attached to this nitrogen of ethyl amine. So, it is ET2 dithiocarbamate anion. So, if it is there, it is DTC minus and it is sodium. So, once you name this in this fashion, you should also be able to write down the name of this particular species. It is the sodium salt of diethyl dithiocarbamate. Dithio means you have two sulfur groups which has been coming from your carbon disulfide liquid, which is organic liquid, unlike your CO2, which is a gas. So, this particular one, so what you find that this is again a chromophoric reagent which can impart some color for photometric determination of some other metal ion. So, it can be your copper 2 plus. What it can do with copper 2 plus, because this particular species, this one is your SS function like that of your DMG function. The DMG function we all know that it is your NN function, NOH, this is O minus and this is OH. This NN function is bound to Ni2 plus, two of them are present to give you NiL2 form. So, this is there. So, when we have this, so what we get over there is that this NN bond, here you have the SS bond in same way. So, this copper 2 plus forming the corresponding chelate with that with 2 Na plus. So, more and more of these organic molecules can be useful for us for the determination of these, and sometimes we find that is not the transition metal ion, but also the corresponding main group ions, also the main group metal ions like lead, because we all know that lead is an industrial pollutant also, it can contaminate the corresponding water. So, in terms of this particular technique, the spectrochemical methods for analyzing the water sample for water pollution, because pollution, it is polluting the air. So, water pollution. So, how to determine this lead like that of your aluminum? So, we have to choose some specific reagent which can react with lead, giving you a corresponding complex. So, we take something that just now we learned something, that how we can see the corresponding molecular structure or the molecule itself, and then how we can name it. Now, we will do in the reverse way, that we name it first, that if the chromophoric reagent is your diphenyl, that means two phenyl groups are present, thio, that means sulfur function is also present, diphenyl, thio and the carbazone, it is a carbazone function, that means you have azone function, that means nitrogen is there, thio means sulfur is there, and diphenyl definitely your pH 2 is there. So, we get some idea, though you are not getting the information that what should be the structure, that means the chelating function. So, it is basically the chelating group, as well as it is a chromophoric reagent to determine the unknown concentration of lead 2 plus. Okay. So, it will be pH then like that of our dithiocarbamate, but it has H. So, it is NN, because this particular part we all know it is coming from phenylhydrazine type of thing. So, pH N NH2 type of thing, and then when it is tautomerizing and in presence of some azo function as well as carbon and sulfur bond, it is double bond C and SH and N double bond N and pH. So, these are the two phenyl functions. So, that is why the name is your corresponding diphenyl. So, this is one phenyl function and this is one phenyl function, and what we see there that it can be H plus or it can be its corresponding sodium salt. So, that immediately tells us it is a different type of corresponding chelating agent, where you have this sulfur will be utilized for your bonding to that lead center and your nitrogen. That is why we have taken this, the name you will not forget the name of these as sulfur and nitrogen. So, if this particular one, because we have to count the corresponding size of the ring, so N, N, C, S and then the metal ion center. So, metal ion center can be put over here. So, this is the group which will be attaching to the center of the metal ion, and this is another group. So, it will be a NS type of bidentate ligand. Then another will be in the opposite direction, giving rise to your Pb, forming a base chelate of like this, plus if these protons are available, you will get 2H plus. So, our basic idea is to develop some coloration by using chromophoric reagent, is that you develop some color out of this, and then we use your spectrophotometer to estimate the corresponding color intensity. That means, we measure the corresponding lambda max and we will take the help of epsilon max, such that we can determine the unknown concentration. Okay, whose concentration is this? This is the concentration of this lead 2 plus. So, we have to correlate everything, and all these things we will see in our next class, that how we can have more than one metal ions also, taking the example of the mixtures, how we can handle. Okay, thank you very much.